Lab 3. The purpose of this lab was to find the mass of a black hole given the mass and position data of a star orbiting it. Assuming the gravitational force is the only force acting upon the star, we will use Newton's second law to relate this to the net force to find the mass. In the process, we will also find the perpendicular and parallel components of momentum and the net force. The result of running a code with these principles through Python gives the mass of the black hole to be almost 2 × 10⁻31 kilograms.
If I destroy this planet, I destroy the gravity field. The rocket. The rocket loses protection and falls into the black hole.
What is a black hole? In the most general sense, is an object of highly compact matter that has a gravitational field so strong that not even light can escape. But for this lab, properties of a black hole other than the mass and the gravitational force are irrelevant. Our star could essentially orbit any large object at the same mass and have the same movement. This topic will be explored further in the what-if discussion. We were given a file containing position coordinates of the star's orbit taken at 1-year intervals, the position of the black hole, and the mass of the star. Using this information, we will find the mass of the black hole. Like past labs, we will use Newton's second law, this time in the form F net equals dp dt. This lab requires a bit more algebra, so first we'll explore momentum, and then we'll get to finding the mass of our black hole. In order to find the change in momentum, first we need to find momentum itself. We can do this by finding velocity from the given position data and multiplying by the mass of the star. Velocity is given by the change in position divided by the change in time. Doing this twice on consecutive time intervals gives initial and final values. This is what that looks like in code. With the final and initial momentum we calculated by multiplying mass by the velocities, we can find dp dt. This is done by subtracting the initial momentum from the final momentum and dividing by the change in time. Then, by the power of Newton's second law, we will say that dp dt equals F net, and we have our net force for the given interval. This is our coded version. Now's the time to mention that dp dt will be calculated on many relatively small positions in a while loop, so these values will vary based off the initial inputs. But wait, that's not all. We're also going to find the parallel and perpendicular components of dp dt. This will tell us if our star is accelerating at a given point, though it tells us nothing about the mass of the black hole. So first, the parallel component. It tells us change in speed. It's given by the change in the magnitude of the momentum over the change in time, times the direction of the momentum, p hat. Following Newton's second law, F net parallel equals dp dt parallel. This is the code. Perpendicular is simpler. Since dp dt is the sum of dp dt parallel and perpendicular, dp dt perpendicular equals dp dt minus dp dt parallel. This value will give relative direction change relating to the curvature of the elliptical orbit. Once more, F net perpendicular equals dp dt perpendicular. This is the coded version. Finally, we calculate the mass. As mentioned, we set F net equal to the force of gravity. Rearranging that formula to equal the mass of the black hole, we get the magnitude of F net times the magnitude of the distance squared over the mass of the star times the universal gravitational constant. By now, all the constants are defined, so we can plug it into our code. This is the coded version. Time to run the module. The arrows correspond to F net and both of its components. As you saw, the magnitudes change with the different relative positions. This is because the star is accelerating as it orbits the black hole. Looking at the data itself, you can see this change, along with the time interval and the mass of the black hole, which stays the same regardless of position. Therefore, the mass of the black hole is found to be 1.99404 times 10 to the 31st kilograms. So, how good is this model? The predicted mass was greater than that of the star. This would induce the star's orbit. While we did take liberties in assuming gravitational force is the only force acting upon the star, the model predicted the same mass independent of the position and thus the net force acting upon the star. This consistency ensures our data to be fairly accurate. What does it mean? How does dp dt and F net differ? We did set them equal to each other after all. Well, the change in momentum components we calculated from algebraic manipulation of observed data. All net force values we found by using a law of nature, and is a relation that can't be calculated directly from gathered data, unlike momentum. It's a difference of concrete and abstract. What if we changed our black hole but everything remained the same? First, revisiting our equation, every variable depends on the star except for the relative position, but even that remains constant in this scenario. So we would not find a new mass unless the star position changed. That concludes the lab. We used Newton's second law to find the mass of a black hole and describe the star's movement with its parallel and perpendicular components. Thanks for watching!